So let's remind ourselves of some polar coordinate stuff. The ideal situation is that if we have something in Cartesian coordinates that looks like a circle or a piece of a circle or anything that's related to a circle, then it would be nice for us to change into polar coordinates, because there's a good chance that our integral then would have constant limits. But we're not necessarily just stuck there. It turns out that if we have a region that can be described better with polar coordinates, then we can still use the polar coordinate transformation even if the limits won't be constant. And we'll take a look at an example of this later. But to start with, let's take a look at that pumpkin. And see if we can solve for this. I don't know. I just saw it on Facebook. I don't usually look at how they do things or who does it. So let's see if we could solve for this. And I was looking at this. The first thing that you probably should look at before you jump into trying to solve a double integral is to look at the limits to see if it would be appropriate to stay in this coordinate system, which is the x and y Cartesian coordinate system, or if it would be more appropriate to change back into polars. And when I look at this, I see these two equations over here that look like they're describing the top and the bottom half of a circle. And so that's going to be our key, is to look at that and convince yourself that it is a circle and that it would be a lot better to do this in polar coordinates. So it looks like this is integrating with respect to y, and that's the inner limit. And the inner limit will go from a negative square root of 4 minus x squared, and that's the bottom half of the circle. And then you have the positive 4 minus x squared, the top half of the circle. And then your y limits out here, or your x limits, are going to go from minus 2 to 2. Constant limits on the outside still applies. And so if we take a look at this in Cartesian coordinates x and y, we have the bottom half of the circle and then the top half of the circle. This circle, by the way, has radius 2. And the way this integral is set up, we're going to integrate with respect to y first, and then your y limits go from the bottom half of the circle to the top half of the circle, and then we're going to make those slices from minus 2 to 2, and so we would recover this whole circle. So instead of doing that now, we pull back to polar. And then what we want to do is basically take a look at this circle and see how we can describe, or take a look at the region and see how we can describe this region in polar coordinates. And so if we can think about it as r and theta, and we can think about the r limits as going from 0 to the region, or the graph of the circle, which is a constant, r is equal to 2. And then we're going to take our angle, start with 0, and then imagine going all the way around. So our slices will be in angles going to 2 pi. Okay? And you don't have to do this, but you can take a look at this combination over here and say, hey, that's just a rectangular region in r and theta. But we don't need to worry about that. What we're concerned about is just rewriting this integral this integral of 2x minus y, so we're going to need to transform, change the x's into r cosine theta and change the y's into r sine theta. We're going from negative 4 minus x squared to 4 minus positive 4 minus x squared with y, and then with x we're going to go from minus 2 to 2. So this is where it becomes polar. We're going to do our double integral. Now the inside function is going to change, and you're going to replace your x with, like I said, with r cosine theta, and then you're going to replace your y with r sine theta. Now remember the transformation, we talked about that last time with the Jacobian transformation. We came out with an extra r, so don't forget your extra r that comes out. And then you have dr, and then this is where you get to put the limits in. The r limits go from 0 to 2 pi, and then you're going to take the, after you get your result, you're going to integrate this with respect to theta, and the theta goes from 0 to 2. Yeah, probably. Let's try that again. So theta goes from 0 to 2 pi, r goes from 0 to 2. Okay? All right. So normally we would be done here, but since I'm going to post this up in Facebook with the answers, I might as well go through, I'll get the answer. So the thing that we can also notice is that the r, there's r's all over the place, but we can factor the r inside, and there will be one r from this parentheses and then another r over here. And then now we can imagine this as being r squared times 2 cosine theta minus sine theta in the integrand. And now if you look at that, they look like they're factors that you can split up. And remember that little, we have constant limits. That's our first criteria. Second criteria is to make sure that your factors can be split up. And then so you can really split this up to 2 separate integrals that you don't have to mix up. And so we can rewrite our first integral with respect to r as an integral with just r squared from 0 to 2. And whatever you get there, you're going to just multiply, simply multiply by a theta integral. And then what your theta integral is 2 cosine theta minus sine theta. d theta from 0 to 2 pi. All right. So the first integral looks like it's just going to be 1/3 r cubed from 0 to 2. Imagine putting 0 in there. You're going to get 0. So this is going to be 2 to the 3rd power over 3. So we should have that integral down. So this one is going to take a little bit more effort, but let's take a look. We're going to multiply by antiderivative cosine is positive sine. sine theta, and there's a 2 out there. The integral of sine is negative sine, so let's make this into a plus, negative, negative. Or why don't we just do it carefully? Cosine theta, and this is going to go from 0 to 2 pi. Let's see. Put 2 pi into sine theta, into the sine function. That's going to be 0. So put 2 pi in there, you get 1. Yeah, so you put 0, you get 0 there again, and then cosine of that is 0. Cosine of 0 is 1. So this is 1 minus 1. This is equal to 0. Looks like this is 8/3 times 0, right? What? I don't know. I think so, yeah.
So if you look at the function of its network of spectral axes,
Yeah.
so it should be as much above as below x.
Yeah, so what he said. Oh, so if we take a look at, Harrison said, if we take a look at the function, which is z is equal to, is it 2x minus y? That, you guys know what that is? What is that? Z is equal to 2x minus y. It's a surface. What's the shape of that surface? It's a plane, right? Bring everything all on one side. Look, there's an x, there's a y, there's a z, then none of them are being raised to the power, so it's a linear type of function. It's a plane. If you bring everything over to one side, z is equal to 2x minus y. Bring everything over to one side. What's your d constant? 0. Equation of a plane, d constant is 0. You have a normal vector that's non-zero, so it's going to have to go through the origin. So a plane going through the origin, and then you take a slice of a circle around it. Imagine how that's going to look like, right? All right, let's actually see it after some hard imagining. I want you guys to be able to imagine this before looking at the picture. So if we were looking at the picture, the integrand is 2x minus y, right? So we can imagine that as a f of x, y, or a z is equal to whatever that function is. Now, imagine our domain also. Our domain is that circle of radius 2, or we want to call it a cylinder because it's going to go up and down. And then, so let's get this set up now. Let's make this transparent. And maybe zoom out a little bit. I think I'm happy with the x and y, so let's just move the z a little bit. So if you imagine the volume of this within the cylinder that's from the surface to the xy plane, you can see that exactly half of it is above the xy plane and exactly half of it is below the xy plane. And so that would cancel each other out, which is that's the reason why we got the result of 0. So this is a good picture to include with our pumpkin. Guess it'll be on the what? I don't know. I think my Facebook friends are not math people. They might get a headache. Kind of like you guys. Might get a headache from looking at too much of this. So we got a negative contribution. We got a positive contribution. So that would be more or less the justification of why we got 0. Okay? Yeah?
If you did want to find this number of contributions, you could just plug in from 0 to pi.
Well, that's a little tricky because we don't know exactly where the cutoff is. So if you really want to look at where the plane changes, I think it changes at an angle, and it might have something to do with y is equal to 2x. So if you cut it there, and then you see where the angles go from there, then you might be able to get a better. Do you guys understand, John Scott? That's actually a good question. What if we just wanted the positive contribution of this? Well, the positive contribution of this would happen for us. Where's a good view?
Yeah, kind of just assume we from 0 to pi because we convert to radians, or because we convert to polar, but I don't know.
No, because you'll miss some stuff.
Yeah, it's not perfect. If we look at that image, like the angle's off from the points.
Yeah. I know what. We'll put an xy plane there. Z is equal to 0. There you go. So if we take a look at this image, you can see where the plane is actually above and below the x-axis. So the blue now, the blue graph is the xy plane. Let's take another picture of this. The blue's not going to work very well. Let's do black. So you have a line y is equal to 2x on the xy plane. If you look at it that way, and this is the plane z is equal to 0, and this is the plane z is equal to 2x minus y. And so this is, if you want to get this in polar coordinates, your angle would be from here to here. That's going to, how about green? This angle over here is the angle, or the two angles that will give you the positive contribution of that plane that's above the xy plane. So whatever this angle is from here to here, and then whatever this angle is from here to here. And then you can use, arctan of rise over run, whatever the slope is. 2 is the slope. And then you should be able to get the angles that way. Okay. You guys gonna get dressed up for Halloween? I usually come to class dressed up and scare students and stuff. I usually dress up as an exam. Anyways. Here's another interesting problem that I saw. There's a couple of problems in Calc 2 that come up in volumes of revolution and slicing and stuff like that. And one of them is like you have a sphere and then you drill a hole through the middle, which is what this is. We'll do this one. There's another one where you have another problem that I like. Let's see. Some Calc 2 volume problems. I like the problem where you have a sphere and then you cut it at some 45-degree angle and then you spin it, so you actually come up with taking off a cone section out of there, which seems like an easy problem. It seems like it's a sphere minus the cone, but there's actually this part of the sphere that gets chopped off. And so this is a good problem to do in polar coordinates. Another problem is when you have a sphere and then you drill a hole, a cylindrical hole through there, and then you ask how much you drilled off or how much is left over. And again, there's this little portion of the sphere that gets cut off that's interesting to look at. The other one is two cylinders intersecting. And then you have to try to figure out whatever that shape is in the middle. That one's a little bit more difficult to do in using double integrals in polar coordinates, but later on we'll get to the idea of triple integrals, and we might be able to get a better visual of that. Actually, all these you can do in triple integrals as well. But this is the one that we're going to take a look at. And so that's this problem over here, where you have a cylindrical drill, a radius, some other radius different from the other radius, bore through a center of a sphere with a slightly bigger radius. So let's see if we could do this problem. And I don't know if you remember doing a problem like this in Calc 2, but in Calculus 2, we have to find like the intersection. We do some volume of revolution or something like that, and then you have to find this intersection, which may or may not be so hard, easy, but then you're integrating this complicated looking square root function. So let's see if we can do this using polar coordinates. And the idea is to imagine what the sphere is going to look like first. So you have a sphere which is x squared plus y squared plus z squared. If we're all just around the origin, that's all nice and easy for us. And then we have the radius is r2. So that's our equation of a sphere. And then the cylindrical drill is going to be given by x squared plus y squared is equal to the radius of the drill. We have to assume that R1 is less than R2, otherwise this isn't going to make too much sense. But if we go with that idea, then we have these two equations. And we can also take advantage of symmetry. If we find the volume up on top here, then we just double that, and then we can find the volume of the bottom as well. So really the function that we're dealing with is the sphere function, and if we want to describe this function as f of xy, then we have to solve for z. And I know it's plus or minus when you solve for z with a square root, but again, if we're just going to take a look at the top part, we'll just consider the positive part. So r2 squared is a constant, minus x squared minus y squared brought to the other side, and then take the square root of z, square root of both sides, and you'll get this as your function. Now it'd be interesting to look at what's happening on the xy plane so we can identify our domain. And if you notice the drawing here already in 3 dimensions, you can kind of see what's going to happen. We have the shape, which in Calc 2 we kind of referred to as a washer, but in math it's called an annulus. And the radii are given by whatever the radius is of the sphere and whatever the radius is of the cylinder. Now, we could try to imagine how to attempt this in Cartesian coordinates, but if you look at the shape of this thing and try to imagine drawing horizontal or vertical lines to see if we can integrate with respect to x first or with respect to y first, you'll see that it's not going to be easy at all. In fact, this is something that can probably be done in like 2 or 3 different integrals, and all the integrals will look kind of complicated, and you have to find all kinds of intersections and stuff. So instead of doing it that way, let's just jump straight into polar coordinates with this setup. Because in polar coordinates, this is going to be really, really easy to describe. It's so easy, it's actually constants. So, what's your R going to go from? You got 2 circles, right? R1, R2. That's it. And then your theta, you just go all the way around to 2 pi, and then that's it. So you have constant limits. Okay? All right. So our volume then will equal to a double integral. We're going to go straight into polar coordinates. Actually, maybe we'll rewrite this double integral first in generic form. R F dA. That's generic. That probably wasn't worth writing. Anyways, in polar form, our f function, remember, is this, and we only need to consider the top half of the circle because we're going to multiply this by 2. So it's going to be R2 squared minus, and then you have x squared plus y squared. And that's r squared, right? Ooh, getting too many r's here. R1, R2, and R. R1 and R2 are constants. R is a variable. So x squared plus y squared, imagine factoring out a negative sign, and you get r squared. All right, now the dx dy, or the dA, that was supposed to be dx dy, will transform because of the Jacobian into having an extra r. And then you'll have a dr, and dr, this is where you start plugging in the limits, r1 to r2, constants r1 and r2, and then the d theta going from 0 to 2 pi. Okay, now constant limits, we can split this up to 2 integrals. And so I'm just going to do a couple more steps. I'm not going to finish this. But we can imagine that our integral from 0 to 2 pi d theta, there's no theta in there, right? So imagine that that's just a constant. You move that out. And then you have an integral from r1 to r2 of the square root of r1, or this is r2, squared minus r squared r dr. And then if you think that this is going to be difficult, that you might need some trig substitutions to do this, well, think again, because this is easier than it seems. So a simple U substitution will get you moving through this problem really quickly, and then you can finish the rest. Okay. Any questions other than what's the answer? All right. So I wanted to do one more problem that did not have constant limits, because that could happen. And I couldn't really think of a good one, so I'm going to have to maybe take a peek at your homework. Ooh, number 10. Well, you don't have any problems with. There it goes. Number 3. So your integral is just a double integral of x dA over some region D, where D is a region in the first quadrant that lies between the two circles. So these two circles are going to be a little tricky to be able to get. But what you can do is you can imagine that this is this is a circle around the origin, a radius 4, but this is a circle that's a little bit offset. The second circle is a little bit offset, and if you want to go through the process of completing the square, I guess that's a 4. So I brought the 4x over to the other side, add 4 to both sides, and then you get x minus 2. Is that 2? Or 4? Plus y squared is equal to 2 squared. So it's moved by the center is now going to be at 2, 0. So got a circle of radius 4 and another circle at 2, 0, a circle of radius 2. And you just want lies between this and the first quadrant. So you just want this little bit over here in the first quadrant. So this is your domain, and now you have to see if you can find a polar coordinate equivalent of this. I suppose this could be done if you solve for x and y, or this looks like it could be done if in Cartesian coordinates if you solve for y for both equations and then integrate.
Right now, outer line has an area of,
Oh no, you're integrating an x. All right, so we want to describe this in polar coordinates, and what we're going to do, let's see if we blow this up a little bit. So this outer circle can be described in polar coordinates as the function r is equal to 4. And then now the tricky part over here is that this function over here is a circle or a piece of the circle that's been offset that goes through the origin and it has radius 2. Now, we didn't really drill into too much of these types of polar coordinate functions, but do you guys happen to know what r is equal to here in polar coordinates? It's cosine theta. And so there's a number here. Is it 4 or 2? I think it might be 4.
Because what happens is you start at 4 at theta equals 0, and then decreases, and then it goes negative.
And then
The other half. Right?
so it would be 4. I don't know. I go between 2, 4, and 8. Theta is equal to 0, r is equal to 4. So, okay, that makes sense. And then r equals 0, which is over here. Well, don't doubt yourself now. Let's go with this one. All right. So this is going to be our function, and imagine your cuts. You know how I usually draw your cuts like this? I'm going to erase this. Except this time you're not wanting the space in here, so you're just wanting this part over here. So this is the region that we're taking a look at, and you can imagine now the region is being is a difference between two R functions at some angle theta that you're making. Say this is your angle theta. Need another color. And your angle theta that you're making, you're only wanting to include some R values that are between two functions. So what we can say here is that your R will go from a lower function. Remember, your R is the radial distance from the origin going in the radial distance outward. And so if you imagine your slices for R going from the origin, you're not going to be in the region until you get to this function. That's this function for cosine theta. And then you're going to be inside of the region until you get out of this function, which is a constant 4. So this will be your limits. These are going to be your limits for R. And then theta goes from where to where? And then theta, we only stop here at pi over 2. So we only go from 0 to pi over 2. Okay? So this is your D explained in polar coordinates, and so we should be able to write your integral now. So your integral is going to be a double integral, and your integrand is x. Remember, x, we're going into polar coordinates already without doing the transformation, just jumping straight into polar coordinates. So all the x's and y's will get changed by those equations. So your x is going to be r cosine theta. There's no y's to put r sine theta in there, so you're done with that. The dA will always have an extra r that pops out. And then your r then goes from not minus, just 4 cosine theta to 4. Those are your r limits. And then your theta limits are going to go from 0 to pi over 2. Okay. I see that I can put the r squareds together, and then I have a cosine theta. Can we break this up? Can we break this? So you can't do this because of the limits. The limits are not constant. We'll just put an X mark over here. Okay. So you got to know when to split it and when not to split it. And there's two basic rules is that your limits are constants all the way through, and your integrand is something that you can factor, split up into a product of one variable and another variable. Okay? All right, so put a dot, dot, dot here for you guys to finish this integral. Okay, question? because I'm looking at where my theta is going to go from, starting and ending points of theta, and then I'm looking at they say here in the first quadrant, so I'm just going to go as far as pi over 2 and not go any further. Although it would be weird if this thing went any farther, because this r goes negative, the calculations for that would be a little bit more difficult. So I'm glad we didn't have to go past pi over 2. Any other questions? Okay. All right, good. We're all good with the polar coordinates then. There'll be more polar coordinates when we jump up to another level of integration in triple integrals, but it'll be called something else. It'll be called cylindrical coordinates, but it's the same thing as polar. We'll see later on. Okay, before we get to triple integrals, though, we have one more section, and that's to consider some of the applications. I think in introducing the applications to double integrals, our transition to triple integrals might be a little smoother instead of always relying on the geometry of it, the area and the volume business. Because we think about the double integrals as finding the volume of something, and so now if we go to triple integrals, what is that? Ew, that would be kind of weird. But they do exist, you know, in somebody's head, that these ideas of finding the volume of a four-dimensional figure, sometimes it's called the hypervolume of things like spheres and rectangles and boxes and stuff. They do exist, even if it's in the mind. So, let's move on to the next section. I know, physics, but we got to do some. But before we get to the mass and density and stuff like that, let's talk about volumes and areas. So it's clear that what we've been doing is finding volumes under a surface, and so we can extend that just a little bit, and this should be fairly understandable based on some of the stuff that we've done in Calc 2, where we find the area between two curves. Here it's like finding the volume between two surfaces. So I won't do an example of this, but imagine you have one surface and then you have another surface down below that's not necessarily the XY plane, and then on the XY plane then you have your region, whether it be a rectangular region or some other region, and then you can find all the space here. The volume of the space can be just given by the difference between the top surface and the bottom surface over that region. Now, if you imagine G is just equal to 0, the XY plane, Z is equal to 0, then it's basically what we've been doing, right? So we can make a note of that special case. Your G of XY, Z, or XY is equal to 0. Then you're just finding the volume under a surface. Exactly what we've been doing. So whether we do this in Cartesian coordinates or polar coordinates, doesn't matter. But that's a short story in volumes. We've already been doing it. Now let's talk about the area. I think the area should have been the first thing we talk about, but this idea of the area is a little bit more, a little trickier to kind of grasp. But if we have an area, we can imagine finding the double integral if we let the function be equal to 1. That's kind of a strange thing to do. But it turns out that it becomes a useful tool for us. So it's not explicitly written here, but you're kind of saying that your z, or your f of xy, is equal to 1. And if your z is equal to 1, imagine how this is going to look like. You have a plane, and then your region on the xy plane is going to be whatever your region in the xy plane is, r on the xy plane. And then if you imagine finding the area under the curve, or area under the surface, and then your surface is just the surface of, it's just a plane of height 1, then you're essentially finding, better if I just copy this. You're just giving it a third dimension in terms of finding a volume. So you're finding the volume of this. So you could think about this, say this thing is some volume that we're measuring in meters. This integral that you would get for this is equal to the volume in cubic whatever measurement that we're using. But since the height is 1, it's like multiplying the area times 1, right? So this is exactly equal to the area. Numerically. In terms of units, the area is in square meters, and what we actually found was something in cubic meters. Well, it turns out that this 1 cubic meter just added another extra meter in the units, but numerically it multiplied it by 1, which didn't really change the problem. So it turns out that you can find the area of a region using double integrals. So numerically you'll get the answer, the correct answer, even though with the units you're going to get an extra unit being multiplied. So does that idea make sense? Okay, so if that idea makes sense, that's something that we can take into a higher dimension. We can actually use triple integrals to find the volume of something. The three-dimensional volume of something. Okay? All right, and we'll get there when we get there. So this is just like a, what do you call those things? Foreshadowing of being able to apply triple integrals. All right, let's see if we can.
Earlier, you could say you're already doing a sort of triple integral finding the volume because you implicitly integrated beforehand the z component.
Yeah. Here are a whole bunch of formulas. So imagine you have a flat plate that's in the shape of D on a two-dimensional region, and then you have a density function. And your density function is given by rho of x, y, and the density function, and we're talking about this and describes something in 2 dimensions. It's the density is in whatever kilograms or whatever you can use for density per square area. Then we have the following definitions. You have the mass, you have the first moments called just the moment in x and y, you have the center of mass, which involves the mass and the moments. Then you have the second moments, which is also known as the moments of inertia, about the x and about the y-axis. But when you're talking about inertia, it's a little bit more interesting to talk about that, about zero, where your plate is some circular type function. And that moment of inertia is given by I sub 0 is equal to this. Okay, so if you just have these formulas, which fortunately in this class you don't have to memorize, but if you're in physics you might have to, you just kind of plug and chug, right? Oh, I forgot to bring a picture. I like to stack rocks up on top of each other. So it's not quite the same, but I want to focus on finding the center of mass. So I have to tell you now that I care more about the first half than the second half. You guys might have homework problems on the second moments, the moments of inertia and stuff like that, but I'm probably not going to give you any test questions on that. You know, the old question, is this going to be on the test? But I might throw one of these other problems up on top. So finding the center of mass. The idea is that you have a two-dimensional plate, and then the center of mass, and then, you know, the plate, when you make a plate out of whatever material, iron or whatever, it could be set so that this is a little heavier, denser than, one side is denser than the other side, or parts of the plate might be denser than another part of the plate. And so if you're trying to balance this, just for fun, you're trying to balance this, the place you would balance it at would be your center of mass. Okay. So finding a center of mass. Let's see if we have some problems that we can steal from your homework. Oh, you guys only have 5 problems here. Yeah, see here you guys got moments of inertia to do. All right, let's do number 1 maybe, or number 2, 1. Let's do number 1. Number 2 looks like it's something that would exercise your polar coordinate skills, so I'll leave you to do that. Find the center of mass of the lamina that occupies the region D, and given with a density function rho. So this is your density function rho. And one of the things that I noticed, rho is generally a function of x and y, but I only see x here. So it looks like the y is not going to be, it's going to be constant, regardless of where the y cut is. So I might be able to use that piece of information. We have the two parabolas, and so if I were to draw that, it looks like it's probably going to be in the first quadrant. And along my x-axis, it's going to change. Along my y-axis, it's going to stay constant. So I'm going to guess that my y-axis, so center of mass for my y-axis is going to be right at the middle. So speaking of the middle, we need to find out where they intersect. And I think they should intersect at 1, 1, and 0, 0. Okay? So we want to integrate this with respect to x or y first. Doesn't matter. It's up to you. Let's see. This is with respect to x. So x will change. Maybe we'll integrate it with respect to x first. And so we would draw a line parallel to the x-axis. Let's do this in black. And then we would find these two functions as x is equal to functions. X is equal to, x is equal to. Oh man, it's 51 already. Why don't we just pick it up from here next time? So we'll do this problem the very first thing tomorrow, and then we'll do a couple more applications, and then we'll jump to triple integrals. You guys will have a quiz on Wednesday? Yeah, Wednesday.